Welcome to Gresham College. My name is Sarah Hart and I'm the Gresham Professor of Geometry. This is the second of my 3 lectures on mathematics and music. My first lecture was on mathematics and musical composition. If you missed that one, don't worry, you can go and watch it on the Gresham YouTube channel whenever you like. This time we're going to explore the mathematics of sound itself. What is sound? How is it produced? Why do some pitches sound nice together and others don't? On the way, we'll find out what's the paradox at the heart of the piano keyboard. Why are the frets on a guitar not equally spaced? And finally, what's the connection between Batman's motorbike and Escher's staircase? So we have a lot to get through. Let's get going. Sound is produced when air vibrates, and our ears can detect that and make an interpretation of it as sound. But if we look at sound waves, we find that it's very hard to, just by looking, discern what is going on. I mean, you have Beethoven's Fifth Symphony being played by an orchestra and white noise, and those two pictures look very similar to each other. In fact, Beethoven's Fifth Symphony is the one here, and the second one down on the picture, and white noise is at the top. But when we listen to the sounds produced by individual instruments, such as the violin and the piano shown on the slides, then we start to see a regularity of the sound. That gives it a frequency, and it's frequency that defines a pitch. So we get a note that has a particular tone, a defined pitch. Now, how do we change the frequency, and how does changing frequency affect the pitch? Well, I want to just show you a very, very simple instrument. I've got one here. It's called a siren whistle. This is the Acme siren whistle, made in the UK. Changing the frequency of the sound you produce does change the pitch. Let's see how. This very simple instrument contains inside it 2 discs, and they have circular perforations in them. One disc is fixed, and the other disc can move. And when you blow into it, that second disc starts rotating around. The harder you blow into it, the faster it will rotate. Now, the effect of that is that when the perforations or the little holes in these pair of discs line up, the air can get through. So the air is sort of coming through at regular intervals. And as the disc spins faster and faster, they line up more often, and so that increases the frequency. But when I stop blowing into it, I'll do it in a moment, when I stop blowing into it, obviously that moving disc will start to slow down, and we will hear a difference in the sound. So let me do that right now to show you. Are you ready? Can you hear that? It's coming down in pitch as the frequency decreases. So this very simple instrument shows us that there is certainly a relationship between frequency and pitch. It looks like the higher the frequency, the higher the pitch of sound that we're hearing. Now, sound has been studied for many hundreds, in fact thousands of years. It goes really back, what we're going to start our story with, to Pythagoras. Now, there's a legend that Pythagoras was walking one day past a blacksmith's forge, and he heard that the hammer heads were hitting the anvils, and he found that sometimes when the hammers hit the anvils, they would make a nice, harmonious sound together, but other times 2 different hammers would sound discordant together. And he was curious as to why this might be, and apparently, he listened for a while, and he realized after a while that when the hammer sizes were in particular small fixed integer ratios, like 2:1 or 3:2, that those sounded pleasing together. And then he went home and tried the same thing with strings and plucking strings on a very simple instrument called a monochord. Now, actually, the blacksmith's shop story is apocryphal. It must be, because the sounds made by bits of metal hitting other bits of metal are governed by different rules than sounds made by when you pluck strings of different lengths. But it's what happened with the strings that is important to us. So let's see what happened with these different sounds that were pleasing together. And there are a few very simple relationships between string lengths that Pythagoras and others since have found make those sounds pleasing when they're played together. So first of all, I should say that we now know if you have a string of a given length, say L, let's say if it produced a frequency F, if you increase the length, the frequency decreases, and there's this inverse relationship. So doubling the length would halve the frequency. Trebling the length divides the frequency by 3. So this inverse relationship is well established. What we're going to do from now on is we're going to talk about frequency rather than lengths of strings, such that we can apply it to different situations, not just Pythagoras' monochord. But the relationships that Pythagoras found are shown on the slide. If you take your initial piece of string of length L and then you halve its length and play the two sounds together, string and half-length string, those two sounds are pleasing together. We'll play you some of these in a moment. Nowadays, and that means the frequency is doubled, nowadays we would say that the second note corresponding to the shorter string, double the frequency, is an octave higher than the first. On the other hand, if you take your string and you double its length, that halves its frequency, and we would now say that the second note was an octave lower than the first. We'll play some of these sounds, as I said, in a moment. The other two ratios written down here, again, very small number ratios. So you take your piece of string and you compare the sound it makes, piece of string, you take your string and your stringed instrument and you compare the sound it makes with one that's 2/3 the length. Well, remember, we have this reciprocal relationship between length and frequency, so the frequency is multiplied by 3/2. That interval nowadays is called a perfect fifth, and those two sounds are pleasing together. Finally, the sound we would now call, the interval we would now call a perfect fourth, is the one where you have a piece of string and then you pluck it and you then take one that's 3/4 the length of your initial string. So that corresponds to a frequency increase of 4/3. Right, so these simple ratios involving the numbers 1, 2, 3, and 4 produce pleasing sounds together. I want to show you some of these and explain why we get these fourths and fifths and octaves. Where do those words come from? Because we're talking about ratios of 2:1 and 3/2 and 4/3. So what's that got to do with anything? This is only, not too much music theory involved, but just to show you the names of the notes on a piano keyboard. I have a very small, it's not a Steinway, it's just a little electric keyboard that has about a 2 to 3 octave. It's about this size range, just to show you some of these sounds. So, to begin with then, on a piano keyboard, there are lots of notes you can play. The closest you can get is when they're adjacent to each other. So we might have a pair of white notes that don't have anything in between. They don't have a black note in between. So I've shown you on the slide, I've highlighted an E next to an F, which if you play them together, they do not sound nice. Ugh, horrible. But that's E, that's F. So they're very close together. We say that they're a semitone apart. Another semitone difference is between B and C. Again, they don't have a black note in between them. Okay, very close. Now, sometimes the white notes do have a black note in between them. And in that case, so I'm playing you an F here, it's labelled F, this one here. And in between the F and the G, there's a note that's a bit higher than F. Here it is. And we call it F sharp, it's a bit higher. And it's also a bit lower than G. There's G, and there's that note again. And so we call it alternatively G flat. So those are the semitones on a keyboard. Now in an octave, altogether, what is an octave? So octaves are the gaps between notes of the same name. So I'll play you some C's here, C. So that's an octave interval. Well, I'll play it properly. And you can see those sound so similar to each other. These two notes sound so similar to each other that we almost think of them as the same thing. They have the same name, they're just in a different register. And when a group of people is singing in unison, for example, then often, the men will be singing an octave lower than the children, say. So these notes are so similar, and they do sound pleasing together, and they're very harmonious. So that's an octave. Now oct means 8, so why is that the case? Well, it's because although there are 12 of these very small gradation semitones that we've mentioned in an octave, let me hear them. That was 12. 13th note is back to where you were. But if you just stick to the white notes for starting on C, and if you replicate that particular pattern of tones and semitones starting on any note, you get what we call the diatonic scale. And I will count through the notes. If this is 1, 2, 3, 4, 5, 6, 7. The 8th note is an octave above where you were. Okay, so the 8th note makes your octave, hence oct. So if the 8th note is an octave interval, then what's the 5th note? Well, let's hear them. 1, 2, 3, 4, 5, count in your heads. That is an interval that we call the perfect fifth, and it's the 5th note of the scale. Let me show you. Here are some fifths marked out on the keyboard. So they sound like this, but you could also have or any other gap of that exact size is one of these perfect fifths, and these are ones that Pythagoreans liked. So this is corresponding to a frequency ratio of 3/2. So you multiply You multiply your first frequency by 3/2, and you get a higher note, and it's here. Okay, so all of those are perfect fifths. And that's one of the ones that the Pythagoreans liked, as well as octaves. The other one that they thought was particularly beautiful was the perfect fourth. And so this is the fourth note of the scale. If you start with a C, then the fourth note will be F. C, D, E, F. Okay, so let's see those. There we are. That's that interval perfect fourth. And of course, you can have a perfect fourth. You just multiply whatever frequency you start with by 4/3. That's the ratio that the Pythagoreans found. Here's another one. Here's another one. And so on. So these ratios are the ones that were thought to be the most beautiful and corresponding to the nicest sounds in combination together. So, what's this paradox at the heart of a piano? Well, on a bigger keyboard than I have here, take a nice big grand piano and start at a very, very low note, for example, a C. And what we're going to do is we're going to keep going up in fifths. So that means we keep multiplying our frequency by 3/2 and produce these nice perfect fifth intervals. So we could start with our C and go to G, and then we could do another one, and then another one. So, and we keep going and keep going. And if you do that, then eventually you start in the first one with a C, say, and then you keep going until you've done 12, and then the 13th one, once if the first one is 1, so if you do 12 whole perfect fifth intervals, you will get back to a C. It's another C a long way up. Okay, so 12 iterations of this, from 1 up to 13, I guess, brings you back to where you were, in the sense that you've got the same note, but just lots of octaves higher. You've got another C. So, okay, fine, but we could then do that jumping, instead of in perfect fifths, we could jump in octaves. So if you do that, you find that a jump of 7 octaves on the piano is the same as a jump of 12 perfect fifths. And this is where we get the term circle of fifths from. If you've ever studied music theory, you will know this term. And I've shown it on the slide here. So we start with our C, we jump up a fifth, we get to a note called G, do it again, do it again, do it again. And at some point you start to hit black notes as well, so you can get all the different tones, all the 12 tones that appear in the octave are represented, each one exactly once in this circle of fifths. And then when you get to the end, from F, going up a perfect fifth from F, that's that same interval again, gets you back to a C, be higher up. That's a circle of fifths. So this is all very lovely. But there's a problem. What is the problem? Well, let's just think what we've had to do to go up 7 octaves. Every time you go up an octave, you double the frequency of your notes. If you start with initially a frequency F, don't mind what it is, then every octave you double. So if you go up 7 octaves, you're going to double 7 times. So the final place you end up with will be 7 doublings later. Okay, so you start at F, and after 7 octaves, you're at 128F, because 128 is 2 to the power 7. Okay, but we also could get there on the piano by going up in fifths, 12 times. So fifths, remember, to go up a perfect fifth, it's a ratio of 3/2. So you multiply your frequency by 3/2. And then that's 1/5, and then to do the next one, you multiply again by 3/2, and again and again and again. So you're going to have to multiply your initial frequency F by 3/2 raised to the power 12. And if you work that out, I'm sure you all are in your head right now, you don't get exactly a whole number. You get about 129.7 times your initial frequency. And those are not the same as each other. They are not the same as each other. And, the Pythagoreans apparently did this experiment with bits of string that they were, not bits of string, strings on their monochord, and they would repeatedly, multiply by frequency by 3/2. In other words, shorten and shorten the string by the appropriate amounts 12 times, and then they took another string on the monochord and halved its length repeatedly until they'd done that 7 times, and the notes that they ended up with were worryingly different. They were almost the same, but not quite. So what's going on? This can't be right, because when we do this on the piano, it does match up exactly. We do end up back at that same high C. So our fifths on the piano, or our octaves, or both, can't be exactly what these Pythagorean fifths are. So what's going on? We have to understand what has been done to make a piano and solve this problem. So, this circle of fifths is not really a circle, it's a spiral, because it doesn't ever come back to a C. Well, in order to have a bit of terminology to discuss this, we're going to introduce a bit of notation called cents, which are not really coins, I just put that picture there. And these were invented by Alexander John Ellis. He was a Victorian person who was working on different kinds of tunings that you could use. And he invented this subdivision of the octave into tiny, tiny increments called cents. And there are 1,200 of them in an octave. Now, let me explain why he did this, or what the motivation is. Our ears experience sound in terms of ratios. So doubling the frequency raises the sound by an octave, for example, and it doesn't matter what the starting frequency is, doubling it will still have that effect that we'll hear a note an octave higher afterwards. So just comparing the absolute difference between frequencies is not helpful, because, for example, if you've got a gap from 100 hertz to 200 hertz, that difference is 100 hertz. Well, we experience that as an interval of 1 octave exactly. Whereas, similarly, if we took the interval from 200 hertz to 400 hertz, that's again a doubling. So we experience that as an interval of 1 octave. But of course, those absolute differences are not the same. In the first case, it's 100 hertz. In the second case, it's 200. So it's not helpful to just talk about subtracting one frequency from the other, because then you get a misleading idea that things are different when really they're the same. So what Ellis did was to create this scale or measurement where that incorporates the fact that we're using ratios and multiplication to compare our frequencies. That's what our ears experience sound as, rather than these absolute differences. So there's a little bit coming up. If you've never seen a logarithm before, just maybe look away for 30 seconds. For those of you who have, you will understand what's about to go on, because what we do is we work in terms of ratios of frequencies. So that's what we care about, not the absolute frequencies, but just their ratios. So if you have a frequency f2 over f1, and you want to find that ratio, then it will be equal to c cents, where here's the ratio. It's 2 to the power c over 1200. So we want to find this c. And we do that by rearranging the equation. And if you have an equation with powers in, exponents, then the way to solve and to find c is to use logarithms. So if you do that, you find that the frequency ratio you're after, if you've got the ratio of r, like 3 over 2 or 2 over 1 for an octave, it corresponds to 1200 log to the base 2 of r cents. So, as I say, don't worry if you don't know what logs are. In a few minutes, we'll be talking about cents, but you won't need to remember the derivation. So the good thing about this is that if you have a ratio, let's say R1, maybe it's 3 over 2, and you've converted that into cents, which is some proportion of an octave, and maybe you've converted it and it's A1 cents. And then you want to follow that by a ratio R2, and that one is, say, A2 cents. So the sort of thing you might want to do is you might want to start at a note, then you might want to go up by a fifth. Okay, that will be multiplied by 3 over 2, and then you might want to go up from that note by, say, a fourth. Okay, and you should find that from the very first note to the last, that's an octave. So a fifth followed by a fourth ought to be an octave. And if we think, what are the ratios? A fifth is 3 over 2, a fourth is 4 over 3, and 3 over 2 times 4 over 3 is 2, okay, which is exactly the octave. So we know that when we follow one interval by another, we are multiplying those ratios. But what do we do with the cent values? Well, if you work out what the new cent value is, it'll involve the logarithm of a product. And anyone who's studied logarithms knows that the logarithm of a product is equal to the sum of the logarithms. So this means that we have turned a multiplication thing into an addition thing. So we can just add our cent values, and that makes all of it work much more easily. So that is what we're going to be using sometimes to compare different tunings. And just to mention before we move on, that difference that we found between 7 octaves and 12 perfect fifths, that 128 versus 129.7, that is about a difference of 22 cents, roughly, between those two tones, very close. 22 cents. Doesn't sound very much, but the human ear is very sensitive. It can detect anything above about a 5 cent difference in tones. So that is very, very sort of discernible and troubling to the human ear, that two notes, they would sound horrible together. They're too close, but they're not the same. We can detect, as I say, anything above about 5, anything up to sort of 10, it's tolerable unless you're, a very, very highly trained professional musician, but 22, everyone can hear, and it's just not good enough. So that's the challenge. How do we get from that horrible difference to the piano keyboard that works so nicely? Well, let's look at what the Pythagoreans did. How did they make the scale? So if you've got an octave difference, and I'm using, the letters of the C major scale, but you could start at any point and do this. So you start with your two notes an octave apart. Okay, the frequency ratio is 2 to 1, right? This higher one is double the frequency because it's an octave higher. And then we can fill in how we're going to tune our Pythagorean piano. We've got a perfect fifth. So this is C is 1, 2, 3, 4, 5. So our perfect fifth is this note G. And a perfect fourth, 1, 2, 3, 4. So our fourth ought to go in here with this note F. So remember, the fifth is 3/2, and the fourth is 4/3. So we'll add those in. Now what are we going to do? Got to fill in some other notes. Okay, well, we can go down a perfect fourth from G. 1, 2, 3, 4. How do we go down? Well, it's like the reverse of going up. So we multiply by 4/3 to go up a perfect fourth, then we ought to multiply by 3/4 to go down a perfect fourth. And if we do that, that's our G. That's our G going to D. And then we can go up a fifth. So let me just show you. We've got C to G, and then G down to D. Here comes the bride. That's one way of doing a fourth. And then from D up to A is a fifth. 1, 2, 3, 4, 5. So we'll put in our A, and then we can go down a fourth to E, and up a fifth to B. So just, compare going from E to B, up a fifth, that's multiplying by 3/2. So 81 times 3 and 64 times 2, yeah, and that fits. So it gets a bit complicated, but this is how we fill in the notes. And we could carry on, these represent the white notes on a piano keyboard, but you could carry on and fill in all the black notes as well by continuing up and down in fourths and fifths. For example, if you wanted that F sharp note that we talked about earlier, you could go up a fifth from your B and create that. So you can get all of these different notes, and you keep getting different notes, and then once you've done 12 different ones, the next one is almost the same as the one you have because of this circle of fifths thing. And this is why we have 12 notes. This is why we divide our octave into 12 parts. Because you can get these 12 things by going up and down in perfect fifths. And then the next one you make is so similar, well, it's similar enough to one you already have that people go, okay, let's be pragmatic and keep those 12. Of course, you might think, well, okay, this isn't good enough. Let's make that 13th note be a different note. And we'll just keep going until we do get equality, and we can have a real circle and not some spiral. And indeed, there were experiments with this. The Pythagoreans experimented with the fact that 53 perfect fifths, one after the other, corresponds closely to 31 octaves. In fact, the difference of those final two notes is only 3.6 cents. You can't detect it with the human ear. It's still not perfect, right? And this is, you don't like things that are almost not quite right. The problem is you can never match up exactly. And the reason is that if you did do that, if you could match up an exact number of perfect fifths with an exact number of octaves, then you would have to have, what's a perfect fifth? It's this 3/2. You'd have to have your initial frequency multiplied by 3/2 to some whole number power. It would have to equal the initial frequency multiplied by 2 to make an octave, an even number power, a power of that. So you can't do this, you can't complete this circle, because 3/2 raised to the power m, say, equaling 2 raised to the power n, say, where m and n are whole numbers, positive integers. If you just rearrange that a bit and multiply up by this 2 to the m on the bottom, you will find that you're trying to solve something like 3 to the power m equals 2 to the power m plus n. And the number on the left there, 3 to the m, is an odd number, and the number on the right, our 2 to some power, is an even number, and no even number equals an odd number. So you're never going to be able to do this, however many octaves and however many fifths you use. You will never be able to, incommensurable things. So perhaps 12 isn't so bad of a compromise after all. But this is why we have a subdivision of our octave into 12. Now, nothing's gone wrong yet, well, apart from the paradox at the heart of the piano. The Pythagorean scale actually was fit for purpose for a long, long time, because people were making music that either was rather simple, sort of simple church music, plain song, without too many weird notes that aren't in our fourths and fifths, or they were using stringed instruments that you can kind of finesse and play with the tuning yourself and not have to worry too much. But then as time passed, music started to develop in several ways that made things difficult for the Pythagorean scale. So I've put sort of pictures indicating a few of these on the slide. The first is that music started to be written down. So Guido d'Arezzo, who we mentioned in my last lecture, who had invented the stave notation, this meant you don't have to just keep your whole thing in your head all the time. You can write down, you can give different parts to different people. It's just a way to become more complicated in terms of music. There's polyphony going on, there's the organ, all that stuff is happening. And music began to get more complicated and involved. And this was, much to the consternation, actually, of certain church authorities. The Cistercian order issued an edict against this flowery kind of music where you were singing in a womanish manner with tinkling and as if imitating the wantonness of minstrels. So that's, very bad, obviously. Let's go back to our simple unison singing. This developed, of course, into the wonderful church music of the Baroque, and I've got Claudio Monteverdi up there, who's the composer of some of the most sublime music of the Baroque era. And he was slated for his licentious modulations and his mountainous collections of cacophonies because of his wonderful harmonies. Another thing that was happening was keyboard instruments were starting to come in. So we get things like spinets and harpsichords and so on, developing over hundreds of years, but even the early instruments had this property that they had a fixed keyboard. So once you had tuned it, that was that, and you can't use a bit of clever fingerwork or whatever to finesse away differences. You tune your keyboard and then the keys are fixed. And so that was another issue. You want to get the tuning right. And if perhaps they didn't quite have 7 octaves in the early days, but if there's going to be a mismatch between different notes, then that's a problem for a fixed keyboard instrument. And the final thing, so that's instruments, the final thing were these newfangled English harmonies that started to come in the 14th century. And proponents of this, very influential composers like John Dunstable, brought these harmonies across to Europe. And so, within 100 years, everyone in Europe was playing these amazing New English harmonies, which are thirds and sixths. So these are new intervals we haven't yet spoken of. Maybe I can play you. So here's a note and then an interval of a fifth up and then another octave higher. Right? Nice little chord there. If I add in, I've now turned that into a major chord and sort of a happy sounding chord. And that note I added in was what's called a major third. That's that little interval. In the C major scale, it would be the note E. On the other hand, you can start with your same austere chord and you can add in a minor chord now. And that's because we've put in a minor third interval. You can have corresponding major sixths and minor sixths. And these new intervals were very popular. Everyone was using them in their music. And there is an issue with the Pythagorean scale, as we will see, because our pure major third that people were starting to introduce is the one that corresponds to a frequency interval of 5/4. So again, a small number ratio, one of these nice little integer ratios. Now, thinking about that cents value, there's 1,200 cents in a whole octave. The pure major third that everyone liked has a value of 386 cents compared to the first note of the octave. And a minor third is a 6/5 ratio, just to say. Now, the Pythagorean major third, the one that we produce between C and E in our Pythagorean scale, actually has a cent value of 408. Of course, you won't remember back to them, but the ratio that was used, derived from fifths and fourths, was 81/64. That's 408 cents, and that is very different from 386. It's different enough to be clearly detectable and people not to like it. They want their pure thirds. So people were trying to come up with what can we do to get around this. And Ramos de Pareja came up with what was called just intonation, and I'll show you what he did. So I've got a comparison there on the slide between the Pythagorean scale and the Ramos scale. And the blue parts are the ones where it stays the same. So Ramos said, we will keep our fifths and our fourths. So that the F and the G, the perfect fourth, perfect fifth, they're fine, they're safe. We'll keep those. And we'll still go down a fourth from G to D, we'll get that. But then we're going to replace some things. We will have a nice 1, 2, 3. This is our major third. We will have the pure third. We'll have that 5/4 ratio. And then to get these other notes A and B, instead of going up fourths and down fifths from other places, we will go up a major third to get from F to A, and we'll go up a major third to get from G to B. So these notes E, A, and B are now redefined. Okay, so this is a change suggested. And of course now, if you play a simple melody in C major, in that exact key on your instrument, you will get your nice thirds and your nice sixths, and you'll also keep your fourths and your fifths. But there is a problem. You may have preserved the fifth between C and G, but you have broken one of the other fifths. You have broken the fifth from D up to A. Now we defined the note A in our Pythagorean scale as the note that's exactly a pure fifth, so a 3/2 ratio from D. So that was how it's defined in the Pythagorean scale. You can already see the A here is different from that. And if you work out the difference, the ratio in this Ramos scale from D to A is now 40/27, not 3/2. It's actually more than 22 cents away from a pure perfect fifth. So this is scandalous. You have broken the saintly perfect fifths. You can't break pure fifths, people said. And you know, there was a lot of argument about, okay, this scale has a major third, but what is the cost? So what are we going to do? How do we fix this? This is not the answer. So the next kind of major step, I mean, there's hundreds of people trying to suggest what to do throughout this time. The next major step, I think, in the story is a practical solution, so a pragmatic solution, which was reported by Francinus Scafurius, whose book Practica Musicae came out in 1486. And he was reporting a solution by local organ makers. So he was the Kapellmeister at Milan Cathedral, and he said, okay, what the organ makers are doing is they're sort of tempering a bit their fifths. And why and how are they doing this? So this practice is called temperament or participator, and this is where we get the word temperament from in music terms. So what they were doing was they were saying, okay, I would normally make my E note. One way of doing it is you keep going up in perfect fifths from C, and once you've done 4 of them, you get to this note E, which is a third above. There's another C there. One C, another one, another one. So you kind of go up 4 perfect fifths, and that gives you your E note. You can then bring that down 2 octaves by multiplying its frequency by a quarter to define that note E that we defined as 81/64. So going back up 2 octaves, 81/64 times 2 again gives you 81/16. That would be the Pythagorean definition of this E. And it's obtained by doing 4 perfect fifth intervals, or pure fifth intervals of 3/2. Okay, so what they were doing, the organ makers, were saying, we actually want this E to be a major third above its nearby C. So we want it to be 5/4 times that C, frequency of that one. Or equivalently, it needs to be exactly 5 times that C 2 octaves below. That's what you want. So what you currently have with your Pythagorean tuning is you have 4 perfect fifths that gives you 81/16. And what you want is a pure major third, which is 2 octaves above the major third here, and that's exactly 5. So you want this note to be 5 times the frequency of your initial starting point, but what you would have in the Pythagorean tuning is 81/16. So what they did was just sort of adjusted their fifths. Each of the fifths, they just made them a bit smaller, just a little bit, in order to get rid of that extra 16th, because 80/16 is exactly 5. Now, what you would need if you want 4 of the same interval to equal multiplying by 5, is you want some number x, such that x to the power 4 is 5. That's what you want. But this obviously is beyond, a 15th century organ maker probably to calculate the fourth root of 5, what they, I'm sure, were doing was just tweaking it a bit so it worked. But this, if you were solving this mathematically, this is the number you would need. You'd need a number whose fourth power was 5, and you could take the fourth root of 5. When you do this, and you just sort of squash your fifths a little bit, the new perfect fifth, so from C up to G, is 697 cents. The pure fifth is 702, so you can't tell. Now, once you add in a few more of these, you start to be able to tell, but it's still, it's okay, it's acceptable. So this is like a reasonable solution. You've got something that just deviates slightly from the pure fifth, but very hard, you can't hear after just one interval of a fifth. This is called mean tone temperament because it involves taking geometric mean of some of the intervals. Now, this is not the perfect solution. Here's why. If we're using our mean tone temperament to tune our keyboard instrument, then let's see what happens when we start with D and we try to play D major. So D major, here's a D. Oh, here it will be in a minute. Okay. That's my D major. And the third note is F sharp. Okay? And that's our major third. Nice major third interval. On the other hand, if we drop down a semitone and try and play the scale of D flat major, which is this note here, we find the fourth note should be G flat, right? So that's a major third down to D, but it's also a perfect fourth down to D flat. Okay, so this note is F sharp and G flat at the same time on a piano, but actually, in mean tone tuning, they are different things. You can't do mean tone tuning to get something that is both F sharp with respect to major third with respect to D and a perfect fourth with respect to D flat. So this is the problem. Our notes are having to do double duty and to be more than one thing, and you can't be all things to all people. This is the basic problem with mean tone temperament. You can maybe get one scale right, but you can't get everything right at once. Now, to fix this, people said, okay, right, I'll just make a keyboard with lots of keys on it, and I'll give you an F sharp and a G flat separately, and then you can't complain. So this is Mersenne here. He wrote a very influential book called Harmonie Universelle in 1636, which included lots of diagrams of keyboards that had extra keys on them, so that you could incorporate all the tunings you like. Here's one that has 27, see, 27 marches sur l'octave, 27 keys in the octave. And there's all sorts of different, you can have all the F sharps and G flats you like and everything else in between to get your tuning right. I mean, these things are hard to make. They are hard to play, they are hard to compose for, but this is the kind of solution that was being thought of to try and make things better and add in everything everyone might want. Ultimately doomed to failure, I would say. But the apotheosis of this was the instrument made by Nicola Vicentino, the archicembalo, I think it's how you pronounce it. Now, this instrument here, I'm going to show you a blown-up version of what's happening down here. It's not a great quality photo, but sorry about that. But maybe you can see, and I'll show you a diagram of it. It has 6 rows of keys. There is so much going on. And there's all these different values you can make, and you can tune it as you desire, such that you can get all these little increments and changes and different things and various kinds of mean tone tuning going on at the same time. This is a very complicated instrument and, did not catch on. What did start to become received wisdom eventually was the idea of equal temperament. So we'd already seen with mean tone, you split equally kind of 4 intervals, you split them equally to get your major third. Why not just do that with the whole octave? Here we see Simon Stevin, who was a proponent of this. He very much was in favour of this system. He said all the others have so many flaws and mismatches and problems and things you have to tweak that, the only solution is equal temperament. So this is where you make all the 12 tones in the octave, all those semitones, exactly equally spaced, the same ratio between each one. So what would that ratio have to be? Well, here's the rub, and this is why it took so long to be adopted. It's psychologically challenging at that time, and for many centuries before that time. Because if you want to divide an interval of an octave, so that is eventually a doubling, my hand should go this way, a doubling of the frequency, equally into 12, then you want some number x whose 12th power is 2. So that interval between each consecutive semitone is going to have to be the 12th root of 2. Now, this is not a rational number. It can't be expressed as a fraction. It's not, you can't make a geometric construction like the square root of 2. Okay, it sort of at least has some familiarity because it's the diagonal of a unit square. But the 12th root of 2, that's very hard to access, and understand what that is. And in an era where, still negative numbers were being treated differently from positive numbers, if you think about how they would solve cubic equations and things, this is a big step. Stefan was definitely in favour of using all kinds of numbers equally, negative numbers, imaginary numbers, irrational numbers. So he was saying, this is clearly the only way we should do this. Everything else has got so many problems. The ancient Greeks were foolish to have persisted with the Pythagorean system, even though they themselves had detected a fatal flaw at the heart of it. But then he did say, you can't blame them because Dutch is the only true language of science. He was Dutch. And so, obviously they were never going to have as much insight as me. But there we are. This is the equal temperament idea. I just want to briefly show you a little comparison of the cent values of our different scales, just so we can see, so the equal temperament, that just divides everything equally. There are 1,200 cents in a whole octave, so each semitone is 100 cents. So a fifth, the perfect fifth, is 7 semitones, so it's 700 cents. And if we compare to the pure fifth, 702, the Pythagorean fifth, obviously the same pure fifth, 702, the mean tone one, 697, these are all very similar. The fourths are undetectably similar. The major third in the equal temperament is different from the pure third of 386, and you can detect it, but it's much better than the Pythagorean 408 approximation. So this, the benefits outweigh the disadvantages really, and this, by now of course is adopted. It took a while though for it to be accepted, because people didn't like losing the pure fifths and making this approximation. Now, once you've accepted equal temperament is the way to go, there are still a couple of challenges. But before we talk about those, I want to just mention, it's a curious fact that actually the first person credited with an equal temperament subdivision of the octave is someone outside of the Western classical music tradition, which is curious because our tradition, where you have stringed instruments mainly, is what kind of gave rise to this idea of dividing into 12 and trying to make it equal. But so this is Chu Tsai-yu, who was working on this kind of arcane problem to do with an ancient religious ritual involving 12 bamboo pipes of different lengths that should each be able to produce, for each month of the year, equally spaced pitches. So he wrote this treatise on pitch pipes in 1584, and he used this approximation, 749 over 500 for a perfect fifth, and that is so close. That's 699.65 or thereabouts cents. That's a really good approximation to the 700 cents of the equal temperament. Okay, so when you're making a musical instrument, what do you actually do? I can't say to my lute maker, give me the 12th root of 2 in all my intervals. You've got to have a practical method for doing this. And this is where Vincenzo Galilei came in, and he was a lutenist. And so he came up with this idea for how we're going to space the frets on our lute. Now, lutes come in all shapes and sizes. This one here is an arch lute. It's bigger than Franz Hauser's lute, but it doesn't matter. It's what we do with it that counts. And in any case, however big or small your lute is, you have the same problem to solve. How am I going to get my semitone intervals in my frets? So what Galilei suggested was to use an old approximation to the semitone that had been put forward by the medieval theorist Boethius, who did not think it was possible to divide even a tone exactly equally because of this sort of objection to irrational numbers, I guess. And so that suggestion of Boethius, which Vincenzo Galilei put forward, was this 18 to 17 ratio. And that's actually a really good approximation, 99 cents. So it's not far off, and it's much easier to say, make an 18 to 17 ratio than it is to try and do the 12th root of 2. With this approximation, a perfect fifth is 693 cents, which, okay, it's not exactly 700, but it's not far off, and you can sort of finesse it a bit with, exactly which side of the fret your finger is on and so on. So it's okay, and for practical purposes, it works well. This was widely adopted. So I just want to show you then the effect of this kind of thing on, actually this is still true even if you use the exactly correct 12th root of 2 ratio. Suppose you're going from the nut to the bridge, and that's to say it's the total distance of 1 meter, for the sake of argument. Then how are we going to produce the first semitone up? So that's kind of the initial note, and then where are you going to put your finger to go up 1 semitone? Where's your first fret? Well, you want to make that 18 to 17 ratio. So remember that our frequency is inversely proportional to the length. So we want to, from the nut to the first fret, we want to make this higher note, and so we want to take off 1/18 of the total, so that what is left, our new higher note, is of 17/18 of the length of the original string. So we take off 1/18, and so that's about 5.56 centimeters, let's say. That's where our first fret goes. Then the distance between the first and the second fret, you've now got this new distance, and you want to take off 1/18 of that. So it's 1/18 of 17/18. So that's a bit smaller, that's 5.25-ish. And then the second to the third fret, 1/18 again of what's left. So 1/18 of this 17/324. So that's about 5 centimeters and so on. And you see this, I mean, the picture on the bottom of the slide just shows a modern guitar, and the neck of a modern guitar. And this explains why these gaps are just slowly decreasing in size as you approach the bridge. So that's a pragmatic solution to tunings. I did want to mention before we move on, because every pianist watching this will be saying, what about the well-tempered clavier, Sarah? Bach's well-tempered clavier, this is a very famous, influential book of 24 preludes and fugues. So that's 12, one for each of the major keys, and then one for each of the minor keys. There was a system called well temperament, invented by Andreas Werkmeister in 1681. And of course, the well-tempered clavier came out in 1722. Did Bach use that? I thought I'd be able to just look up and tell you the answer to this. But there's a whole world of discussion and argument about exactly what he'd used. Some people say, yes, he used that. Others say, well, no, it doesn't mean that. It means just that the keyboard you're using, it has been tuned very well. So it just means that. Some people think he was in favour of equal temperament, and he did this by showing, here are my 12 or 24 different things, and it doesn't matter which key you play in, I can do whatever I like in any key. Others think not. So I don't think perhaps we'll ever know for sure, but yes, there was a system called well temperament. It was one of many alternative things that are being proposed for hundreds of years, really. Okay, well, I want to move on now for the rest of the talk and discuss really the question we haven't asked ourselves yet, which is, okay, we know these particular frequency ratios sound nice, but why do they sound nice together? We haven't decided, we just said that they did, but we didn't say why. So things have been known for hundreds of years about how vibrating strings behave and what we can do to them to change the frequency. So the first, I guess, written down rule about this was Vincenzo Galilei, we heard earlier from him with his lutes, discovered that for vibrating strings, the pitch or the frequency that they produce is proportional to the square root of the tension in the string. So that's actually thought to be the first square root law known. Then Galileo Galilei, his son, formulated further laws, and so too did Mersenne, who we also saw earlier, and he actually included experimental evidence that he had verified these experimentally, and I think that's why the laws have got his name. They're known as Mersenne's laws, and are encapsulated by a little equation that says, it shows you that the frequency of a vibrating string is inversely proportional to the length, so we've already noted that, so it's got 1/2L, and then there's a square root of the tension on the top, and on the bottom, that mu, that's the linear density, the mass per meter, per linear meter. So all of those things influence the frequency that a string makes. And Mersenne experimented, so what he did was he'd get these, he had a monochord as well, and he had pieces of string, and he would vary the tension and the length and so on and so on. And how do you actually measure frequency? Well, what he did was he would get some, vibrating string, and then he wanted to understand its frequency. He would repeatedly double the length until he could actually physically see and count the vibrations. And then he could work backwards to what the original frequency had been. We have better ways of measuring frequency now. Okay, but then why are the ratios that we like, why are those ratios of frequencies harmonious? Well, Galileo had a theory. So this is him. His theory was to do with pendulums, and he's a sort of pendulum expert, right? This is a picture of him, age 19, looking at these swinging incense burners in Pisa Cathedral and realizing that there's a law of pendulums and working out what that was. Now, there's slightly something wrong with this story as well, because when Galileo was 19, it was still 4 years before those incense burners were installed at Pisa Cathedral. But anyway, it's a nice story. What Galileo said was that, okay, imagine two pendulums swinging, and if they're both swinging at the same rate, then that looks very nice together. Okay, we may set them swinging at the same point. They look nice together, so that's all good. And if one's swinging twice as fast as the other, which I can't do, then that would look nice too, because they'd meet up very regularly. And that corresponds to our octave interval. And if one's swinging 3 full times in the time the other takes to do 2, then that also looks good. So it's these small integer relationships. They look nice if they were pendulums, so the sounds are nice together. Doesn't really work, doesn't stand up to argument. I mean, there's an obvious link between pendulums and sound anyway, but also ratios like 5/4 and 6/5 sound nice. They're our major and minor thirds, and 8/5, that's a sixth. They sound nice, but something like 7/5 doesn't. So why would that be? So this doesn't really work. Galileo said the worst possible ratio would be one where it was an irrational number ratio, so something like 1 to √2. Now, we don't hear that much in music, and certainly not in Galileo's time, but of course everyone now will recognise that interval, 1 to √2. It's called a tritone, because if you've ever seen The Simpsons, the cartoon, it's at the beginning of their song. The Simpsons. So we all know what tritones are, but yeah, this explanation of Galileo's is not really very helpful. So, well, other people were asking this question. Samuel Pepys was interested in this, and this is my claim. Samuel Pepys went to a Gresham geometry lecture about this, and I'm just doing another one a few hundred years later, the sequel. So in April 1668, he went with Lord Brunker, who was then president of the Royal Society, to the King's Head Tavern by Chancery Lane, and did hear of Mr. Hooke, the then Gresham Professor of Geometry, and my lord, an account of the reason of concords and discords in music, which they say is from the equality of vibrations, but I am not satisfied in it, but will at my leisure think of it more. Okay, so next day, like any sensible person, he goes to try and find it in a book. He went by coach to Duck Lane to look out for Mersenne, who we were talking about earlier, his book, in French, but it's not to be had. So, oh dear, so he's left to his own devices. January 1669, this is very optimistic, and I'm in the right way of unfolding the mystery of this matter, better than ever yet. Fantastic. So what did he come up with? He never mentioned it in his diary again, is what happened. So, he obviously did not quite manage to solve the problem of harmony and concords and discords in music. Well, let's see if we can add a bit to the discussion. And the first bit we want to add is called the wave equation. So imagine you've got, a violin or something where there's a string fixed at both ends, and then you sort of disturb it at some point, you pluck it or whatever, you move it, and then it starts vibrating. So the sort of setup is your string is fixed at both ends, you disturb it at some time, t equals 0, and then you're interested in kind of as you move along the string, so the horizontal displacement x along the string from one of the fixed ends to the other, what's happening vertically? The vertical displacement y, what is happening? And obviously that's going to depend both on the time t and on your position along the string. So this will be a function, this vertical displacement will be a function of two variables, the horizontal, how far you are on the string x, and the time. Now I'm just going to show you this equation that governs that behaviour. And again, I'm aware there are symbols in that equation that people may not recognise, that's completely fine. I want to sort of show you the shape of it at least. So for those who do recognise a partial derivative, that's what these things are. But what this equation is saying is that there's some sort of constant thing about the string, it's tension divided by its density, so that doesn't change. Then this thing on the left is telling you how the vertical displacement y changes with respect to time. It's sort of rate of change, very roughly speaking, in terms of time. And then on the right, you've got a similar expression, but now we're talking about how the change is determined by the horizontal distance. So these two things, what this equation said is that these two things, how it changes with time and how it changes with distance, are very closely related. Now, the first step in solving this came from D'Alembert, and what he said was actually a solution to this kind of equation is comprised of two halves. It's got to have a wave, which we'll call A, that is moving along the string from left to right. And as it does that, it'll get to the end. And when it gets to the end, what happens? We can't sort of destroy energy. Conservation of energy happens. That end is fixed, so it can't sort of fall off the end of the string. So the only real thing you can do is, if you're preserving the fixedness of the string, is that wave has to sort of turn upside down and reverse its direction, so that it kind of cancels itself out at the end of the string. So then it sort of goes upside down and reverses and becomes this wave B that starts moving backwards and upside down back along the string. So the solution is a wave A and a wave B, but it's a periodic solution, because if this wave A moves along and then flips and comes back and then flips again, then every twice the length of the string, you repeat where you were, you get back to where you were. And so wave A does that, and wave B does it as well, because wave B is just wave A upside down and backwards. So that's what happens. You get this periodic solution. So what D'Alembert found was that all the solutions of this are periodic. And then Fourier made a great breakthrough. He proved that any periodic function like this can be broken up as a combination of sine waves, the simplest kind of periodic function. So I've shown you a few of these here. So the first one is like goes half the sine wave in one direction and then the other half coming back. Then you've got a full sine wave and then one coming back, and 3 and 4 and so on. And these correspond to frequencies, initial frequency F, then double it, treble it, and so on. So frequencies F is the fundamental one, but then there are also solutions at 2F, 3F, all the integer multiples of your initial F. So different instruments will have different combinations of these waves. So every sound will be just some linear combination of these sine waves with integer multiples of frequencies. There's also an initial transient sound that we call that's important as well to the sound of the instrument. In other instruments, just quickly mention, things like flutes, they're open at both ends. You blow in the top, or like along somewhere along the way. They're open at both ends, so the equation, the boundary conditions there is that the pressure has to be equal to the ambient pressure at both ends. So you get the same sort of thing, and you get the same equations. With a clarinet, something like that, it's closed at one end where you blow in, open at the other. So at that open end, the pressure has to equal the ambient pressure. So that sort of setup favours odd multiples of the fundamental frequency, these half sine waves. Of course, there are other instruments, things like drums. You then have a two-dimensional wave equation, some solutions of which are shown here. But the net effect, or what we want to talk about, is that when you have these solutions, you get your initial frequency, a fundamental frequency, and then various amounts of multiples of that. So you've got this frequency F, and then they call them overtones or harmonics. And I've just showed you, for those of you who can read music, there's the first few harmonics. So the first one is double the frequency, you've gone up an octave. Then the next one is 3 times the frequency. So that corresponds to going up an octave and then a perfect fifth up, and then so on and so on. And it gets quieter and quieter as you go up. So why do some sounds sound nice together? Well, it's because they share the same harmonics. So the harmonics of 2F, if you've got initial frequency F, then 2F is going up an octave. Its harmonics are a lot in common with the harmonics of F. Every harmonic of 2F will also be a harmonic of F, because every multiple of 2F is a multiple of F. So they've got loads and loads of harmonics in common. That's why they sound nice together. Our ears sort of expect to hear them together in some way. Similarly, this 3 over 2F, which is a perfect fifth above F, it has many harmonics in common with F as well. If you double it, you get 3F, that's a harmonic of F. So any kind of even integer multiple of 3 over 2F will also be a harmonic that's in common with F. So they've got half their harmonics in common. So this is a really plausible argument why these are sounding nice together. And that really answers that question about why some things sound good and others don't. To finish, I want to mention that now we understand how all these things work, and we understand about harmonics and overtones, we can actually use this to create some really weird auditory effects, like auditory illusions. So if you're interested in this, go and look up the work of Roger Shepard and Diana Deutsch, among others. I want to show you this thing called the Shepard scale. So how that is made, I'll play it in a minute, is that you create tones out of harmonics that are spaced 1 octave apart, and instead of, as usual, the lowest note being the loudest, fundamental frequency being the loudest, it's the ones in the middle that are the loudest. And that does a strange thing to your ear, as we all hear. Just watch what happens when this ball bounces up this impossible Penrose-Escher staircase. There it goes. It's going up. Still going up. Up some more. And still up. And up. It's going to go up forever. So this is exactly the same kind of illusion as the Escher staircase. It appears to keep rising forever. And this, if you take a glissando version of this, a continuous version, was used by Christopher Nolan in his film The Dark Knight in 2008 for the sound of Batman's motorbike, because he wanted it to be always accelerating, which corresponds to a constantly rising tone, which of course is impossible to do forever. But with one of these Shepard glissandos, you can actually cause that effect to happen. So that's how we get to Batman's motorbike. Well, I hope you've enjoyed this brief tour of the mathematics of sound. It went there. If you have, fear not, there's another lecture coming in January, which will be my third lecture on this topic, January the 5th at 1 p.m. You can go and sign up at Gresham. It's about the mathematics of bell ringing. Of course, if you haven't yet seen my first lecture, you can go ahead and watch that on YouTube right away. For those watching the live stream right now, I'll be available in the text chat afterwards to answer any questions you might have, so go ahead and ask those. But it just remains for me to say thank you very much for watching, and I hope to see you next time.